This is Lab 4, Spring Mass Data. Introduction. The focus of this experiment is to determine how to identify, calculate, and computationally model oscillation. The purpose of this was to use elements such as periods of oscillation, Hooke's law, and potential energy to create a computational model of oscillation. Some of the main physics ideas were period of oscillation, Hooke's law, potential spring energy, and potential energy of gravity, as demonstrated with these equations. Brief overview. The lab demonstrates that the LO value for the spring is 0.013 meters and that K is equal to 5.745 Newton meters. Procedure. The first step was to use a tracker to analyze the given video oscillation of a spring, then export the data into an Excel sheet, modify the code to match the data in tracker, and compare the two. Using tracker, here's a screenshot of me using tracker. Here's just some data that I had, here's some equations that I had to use to determine what the K value was using period of oscillation. And then here was finding the LO value. Coding, here is a couple of screenshots of my coding where we can see here the mass was updated, position, velocity, gravity, all that. And then here is the main focus of the editing of this section of coding. And then this is going to be the rest. This was my graph. It is very wrong. It oscillated while it was going in motion, but I'm not too sure why it only presented itself at the end. What does it mean? For your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. No, because my graph did not come out right. If there was more oscillation on my red, blue, and green lines, and my orange line was straight on the 0 for the x-axis. Using the data you obtain in tracker, make two separate estimates of oscillation periods. First, by eliminating the period of oscillation from the x position data, and second, by eliminating the period of oscillation from the y position data. Compare the two, eliminate and discuss estimates and discuss. The x position would be the 1.662 seconds as previously shown in the slides. I believe the y value would be the same because the oscillations go hand in hand despite their different axes. So when calculating oscillations, you count the number of oscillations, and there was the same on both the x and the y, so they would essentially be the same, but despite them being flipped, they're still going to be the same because time cannot be represented negatively. Possible errors. My code was definitely incorrect, and like I said before, it went through and oscillated, but in the final presentation, it did not present the oscillations. Conclusions for this lab demonstrated to us how to analyze, computate, and create models for oscillation.